Okay, so how many of you would consider yourself experts on derivatives? You're in Calculus 3. How many of you would consider yourself pretty good taking derivatives? You know the rules, and you loves the power rule. And gee, I thought more of you would maybe say, how many of you think maybe you're good with derivatives? I mean, you're comfortable. Okay, Andrew's comfortable, Gordon's comfortable, Juliana, Charles, good. And very good, very good. Excellent, excellent. I didn't have time to read all the names, but it's basically all of you. Okay, Malik, I understand. I understand. Learning is a constant experience. Well, partial derivatives are, I'm going to show you the definition of what a partial derivative is for a function of two variables. So you see here, you have, I mean, you see that you have like the limit as h goes to 0 of a quotient. But you have the two definitions differ. Well, you're used to this. Okay, what you're used to, let me just show on the whiteboard what you're used to. Okay, hold on here. If I can find my pen here. You're used to this. Okay, one moment. Yeah, you're used to f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. How many recall that definition from Calculus 1? Good. And it's based on this definition that you derived all your derivative rules. So, but now, instead of a function of one variable, we have a function of two variables. And we can even have a function, functions of more variables, function of 3 variables. So the definition of a partial derivative is similar to this definition, but we have to adjust it a little bit for the fact that we have a function, let's say in this case we have a function of 2 variables. Okay, so, whoops, hold on, I don't want to do that. For God's sakes. Hold on, don't look. There we go. Okay, so let me see. Hold on here. Let me just ask, did my video show on the screen at all? I have my shirt off, so okay, all right, good. All right, I'm a little warm. I've got to save on air conditioning class, so I had my shirt off. Good, I'm glad. All right, so let me see here. All right, so let me go back here to where we were. Okay, let me go back to the thing. Okay, so here's, you see now the definition of partial derivative. So the f sub x stands for the partial derivative of f with respect to x. And there you are you're holding y constant and letting x change, x plus h to x. And then the second equation is the partial derivative of f with respect to y. There, you are holding the x constant and letting y change. So in one, basically the first partial derivative, the partial derivative of f with respect to x, you are studying how the function changes with respect to x for a certain y value that you're holding constant. For the second partial derivative, the partial derivative of f with respect to y, there you are holding the y variable you're holding the x variable constant, and you're studying how the function or the surface changes with respect to y. and you're holding x fixed. So these are how partial derivatives are defined. And fortunately, all the derivative rules that you learn will be preserved with the partial derivative rules. And if you have a function of more than two variables, let me just show you that, because I do want to get to an example. We do need to get to an example here, and I want to try to do this as good as I can here. Hold on here. Sorry, I'll find it. Yeah, here you have a partial derivative, a first partial derivative, where you have a function of three variables. And the analogy is the same. If you have a function of three variables and you're differentiating that function with respect to x, you hold the y and the z constant, and you let x change. So you're finding slopes of tangent lines, so to speak, well, you're finding rates of change with respect to different variables. That's what you're doing. Now, what I want to do here is I'd like to do at least one example with you here. Okay, one example. Let me give you a moment to copy this example down, and then we'll get right to the solution, okay? So hopefully we might go a few minutes over. It'll be in the recording, but if you can stay just a few extra minutes, that would be great. All right, let me let you copy this. This is notation, by the way, for partial derivative. This is like, how many remember Leibniz notation? Like, you know, dy, dx. So in other words, for like in calculus, you could have, you know, calculus 1, calculus 2. Yeah, that's called omega. No, wait a minute. No, that's not omega. That's called var. This is called var theta. That's the Greek symbol var theta. So, like, you know, in calculus 1, you have f prime of x. You have df dx, right? You have Leibniz notation. This is the Leibniz notation, df dx. But when you're doing partial derivatives, you use this symbol, okay, for a partial derivative. Okay, so like what I'm trying to say here is that if for instance, if w were just a function of one variable, then you would have dw dx. dw dx equals f prime of x. Okay, and the dw dx is the Leibniz notation. But this is when you have a function of one variable. When you have, in this case, w is a function of three variables, you have to use the var theta symbols, because these are partial derivatives. Okay, are there any questions on that? Okay, let's go ahead and get to the solution here. Okay, so mark this moment. This is your first time taking partial derivatives. Okay, so here, first we're doing the partial derivative of w. Yay, that's right, Ian. This is like when you got your driver's license. This is how important this is. I'm doing the partial derivative of w with respect to x. This means that I'm going to hold the variables y and z constant. They get held constant. I treat them as constants. So I'm going to take the derivative like you would take the derivative in calculus 1 or 2, but the variables y and z are held constant. So that means this variable z can be brought out in front of the derivative, because z is, we're treating it like a constant. Okay. Now I take the partial derivative of this function, and I'm going to use the chain rule. So there are two functions. The outer function is the exponential function, and the inner function is the function x times y times z. So by the chain rule, the derivative of the exponential function, is just itself, and then the derivative of the function x, y, z is just the derivative of x is 1, and then the y and z are treated like constants. So already Hyunyu's liking this. And this is your answer. Okay. Please let me know if you have any questions. Okay, are we ready? Are we ready to go to the next one? The next partial derivative? Okay, let's go to the next one. So here now, we're doing the partial derivative of this w function, okay, with respect to y. So now you're going to hold the x and the z constant. This means the z can be brought out in front of the derivative. And I'm going to now use the chain rule to take the partial derivative of the function e to the power xyz with respect to y. What I do here, to make it look a little easier for you, xyz, okay, is the same as y times x times z. I just did that because then, you know, the derivative of y is 1, and then the x and z are constants. It isn't really necessary to do what I did here, but I just, you know, thought it'd make it look a little easier for you. And this is our partial derivative. Take a moment to look at it. Are there any questions? Hyunyu's good, okay. All right, may I go to the next one? Well, Ian is right. The last one is the hardest one. All right, let's get to the last one then. Here's the partial derivative of w with respect to z. Now we're holding the x and the y constant. So what we're doing is we're finding the rate of change of this function with respect to z for some fixed values of x and y. Well, now we can't pull the z out in front of the derivative because it's not treated like a constant anymore. It's varying. So really we have two functions of z that are being multiplied together. You have the z itself, and then you have this e to the xyz power. Well, you're going to have to use the product rule on that. The derivative of z is equal to 1, and then you leave the second function alone. I mean, this is what we're doing here is like, you know, f prime times g plus f times g prime. I mean, effectively, that's what you're doing, only it's with, you know, partial derivatives. So we use the product rule. Are there any questions on the product rule here? And then I have to do the partial derivative of this function with respect to z, and I do that down here, right here, actually. I mean, it's really beautiful stuff. Quite beautiful stuff, really, and essential for what you're going to learn. And so then the final answer I write like this. And I'm sharing my video with you to show you I have my shirt back on now. All right. Are there any questions on this problem? Hyunwoo's good. Who's feeling good about it? Who feels good? Ellie? Ian, good enough. All right. And we'll certainly get into, we'll talk more. Sure. Andrew's good. Excellent. And we'll talk more about partial derivatives next week on you know, Monday's class. You know, I'll stop the recording here.